Hey everyone, I'm Nick, and welcome to another episode of Tools of the Trade. So in this episode of the series, we're going to be talking about Google Benchmark. So Google Benchmark is a library for microbenchmarking, and it's something that I use fairly frequently on this channel and in a number of my series. So to get started with Google Benchmark, there's just a few setup things that you need to do. So you can find all the information about downloading and installing Google Benchmark from the README inside of the repository. So that's located at github.com/Google/benchmark. I'll link to that below. And inside of the README, you can see there's some links to some resources, the build requirements and the platform-specific build instructions, and the installation instructions. So this is exactly what I followed to set it up on my system, which is a Linux machine. You basically just clone the benchmark repository, you clone Google Test as well, and then you basically run cmake and then make. And then optionally, if you want to install it globally, which I did, you can just run sudo make install. So nothing too complicated here. And so after you have all this set up, you can begin writing your first micro benchmark. And that's what we're going to go over today. So how do you actually get started writing your own micro benchmarks? So let's say, let's create a new file called mybench.cpp. And let's say we want to benchmark something like benchmark stood accumulate. So let's say we want to benchmark the time it takes to sum the contents of a vector. So we have some vector of integers, and we want to figure out what's the sum of all the values in there. Okay, so the first thing we need to do here when we're working with Google Benchmark is to include a header for the benchmark library. So that's just going to be this benchmark /benchmark.h header. You can just include it directly like this if you have it already installed. If you've installed it globally. Otherwise, you'll need to provide a path to this header from the repository that you cloned, where you built the benchmark library. So from there, our benchmarks are set up by, we write a static void function, right? And that's going to basically be, represent our benchmark. So, we don't have to take care of all the boilerplate code for writing a main function, writing all the code to collect the timing information, or the code to repeatedly run our code and run our benchmark multiple times so we can get stable timing results. All of that is taken care of by the library. All we really need to focus on is functionally what are we trying to time. Okay, so let's write a static void function, and we can name this whatever we want. So I'll name it something like accumulate bench. So give it a meaningful name, and into this function we're going to be passing a benchmark state object. So that gets passed to every single one of our benchmarks. So it's just this benchmark state object, and you can see here in kind of the description, it's passed a running benchmark and contains a state for the benchmark to use. So if we want to pass in, any arguments to our benchmark, we can do it through the state object. We pass this in by reference. So we'll just call it S. Now, to mark that we want to run this benchmark when we run the executable, we have to use this macro called benchmark. And we just pass in the name of the benchmark to this macro. So using this benchmark macro, we just pass in accumulate bench. And then because this is still a C++ program, we need a main function. But like I said earlier, we don't need to write it ourselves. So we can just replace that with a call to benchmark main, right? And that basically replaces our main function for this C++ application. Okay, so we have kind of a framework for a benchmark. Now we can begin writing our setup code. So all we really need to focus on is writing our setup code and then marking where we want to start collecting timing information. Okay, so the first thing we need to do is set up the number of elements that we actually want to accumulate, right? So how many elements do we want in our vector? So here I'll just say, auto n is equal to 1 shifted over 10 times. So this is just going to be 1024 elements, or 2 to the 10. So let's put that in our comments. So the next thing we need to do is create a vector of random number. So let's say I want to, that's going to be my input to stood accumulate. So let's include the headers we're going to need for that. So we're going to need vector for our stood vector. We're going to need something like C standard lib, or something from the random header for random numbers. And then I'm going to go ahead and include algorithm, so I can use stood generate. And I'll use Clang format to format everything. Okay, so let's create a vector of integers. So stood vector of int, we'll call it v, we'll say of in numbers. So I'll create a vector of in zeros. And then I can just use something like std, generate, go from the beginning of the vector to the end of the vector. I'm going to apply a lambda to every single element, which is just going to return rand mod 100, right? So it'll be a random number from 0 to 99 inclusive. Okay, so that's most of our setup code. And then we'll need some variable for our result. So we'll just say that, our int result, we'll initialize it to 0 down here. So that's where we're going to store the result of std accumulate. Okay, so the only thing we have left to do in our benchmark is to mark where we want to start collecting timing information. So far, this is all just setup code. So where we want to collect timing information will be inside of a range-based for loop. So this will be our main timing loop, right? And the syntax of this range-based for loop is typically for auto underscore in s, right? So anything that's within this for loop, that's what we're going to be running multiple times, or rather Google Benchmark is going to take care of running this code multiple times and collecting timing information about how long these iterations take. So inside of here, I can just say, the result of is equal to std accumulate. I'm going to need to go ahead and include another header here. So this will be the numeric header. That's where std accumulate is located. So std accumulate from the beginning of the vector to the end of the vector. I'm going to sum up all the numbers into 0 and return that sum into result. Now there's something that's obviously, or maybe not so obviously, might happen here, and that comes with this integer result here, right? It's very likely that this is just going to get optimized away because all we do is assign into result and we never use the value of result. So this is a very common thing to kind of worry about when you're doing microbenchmarks. Because you might be cutting away all the complexity of your real world code when you're trying to cram it into a microbenchmark, you may wind up with situations where a compiler ends up optimizing things a way that you don't want it to. All right, and this is exactly a case like this. So, in real world code, you're not just storing, the result of std accumulate into kind of a dead number right here. You're using it later on in your application, but that's not what we're doing right here in this benchmark. So, if this happens, right, and if your compiler really does optimize this away, let's see what the compiler might give you. But first, we actually need to compile this, of course. So how do you compile one of these Google benchmarks? Well, if you've installed everything globally, like I have, it's pretty simple. You just use a compiler, whatever you built your benchmark library with. So here I'm using G++, pass in my file mybench.cpp, and I'll need to link against two things. I'll need to link against lib benchmark and libpthread. That's just requirements of Google Benchmark. And then I can do whatever optimization flags I want. So O3 optimization, I'll usually use something like -march equals native, -mtune equals native. Turn on link time optimization, use the linker plugin, and we'll just call our output file something like bench. So it's very likely, like I said just before, that the compiler will get rid of this code. So what happens when your compiler completely gets rid of code like this? What happens with our benchmark? Well, you'll probably see something like this, right? So you get some information that gets printed out, about your local machine. So, the number of cores you have, the frequency, size of your L1 cache, your L2 cache, your L3 cache, and then you'll get, whatever benchmarks were run, the wall clock time, the CPU time, and then the number of iterations that were run. So that's iterations. How many times did it run that for loop where we placed our, what we wanted to time? So if you see something like this where, it took 0 nanoseconds and it ran for 1 billion iterations, this is just very likely that, what happened was your compiler just completely got rid of your code inside of your timing loop. So how do you get around this? So there's a couple ways. So one kind of a hacky way is you just mark this as volatile and kind of tie the hands of the compiler and keep it from optimizing this away. So, if we mark this result int as volatile, if we go ahead and recompile this and we run this, we start getting some results. So you can see that our accumulate bench took 44.8 nanoseconds and it ran for something on the order of 15 going on 16 million iterations. So it's not just running and collecting timing for doing stood accumulate for one iteration. It does it for some number of iterations. So in this case, it did it for 15 million iterations, and then it decided to stop. Okay, so what are some other ways we can keep the compiler from optimizing away our code? So another kind of way is to use dynamically allocated memory. So if we turn result into a pointer to an integer, and we just say this is equal to new int, and then we change down here, we are storing stood accumulate into this piece of dynamically allocated memory. And let's not forget to delete result at the very end, so freeing that memory. This is one way that you can typically get around your compiler optimizing away code. So if you're doing something like, copying from one vector to another vector, or storing, from one vector into another vector, your compiler most often will not get rid of that code. So let's go ahead and try this and see what happens. So we can run bench again, and you see we get just about the same result, 42.6 nanoseconds. It's very likely you won't get the exactly the same results each iteration, or every single time you run a benchmark. It could change, and the longer your benchmarks run, you might get even wider swings and the timing results, just depending on the load of the system. So that's something to kind of watch out for as well. But there's one much more Google benchmark way that we can keep this result from being optimized away. And that's by using something that's built into Google Benchmark. And that's going to be this benchmark : do not optimize. Right? And we can just wrap this entire expression inside of benchmark do not optimize. So what is this actually doing? Is this turning off all of our optimizations? Is it going to get rid of everything and just leave us with some very unoptimized code? No, not really. All this really does is force the result of this expression to be stored into memory. So we should get all our optimizations that are here. So if the code was going to be vectorized, it should still be vectorized. It's just going to store the result into memory this time. So now we can avoid mucking around with our code and throwing volatile keyword around or dynamically allocating memory when we don't have to. Okay, so let's go ahead and recompile this and see the results. So now it took about 44.2 nanoseconds. So we got fairly consistent results for all three implementations. Let's take a look at the assembly. A good thing to do whenever you're writing these benchmarks is to do a sanity check on what's actually going on underneath the hood. Right? That'll help you make a little more sense as to why is my code running faster or slower. And for something like a microbenchmark, especially for something as simple as stood accumulate, it should be fairly easy to understand. Right? Maybe not in some other circumstances, but for something like this, it's not a bad idea to look at the assembly. So let's do perf record on our benchmark, and then perf report to look at the report, and we'll go into accumulate bench, and you can see most of our time is being spent in this one loop right here. So what are we doing here? Looks like we're doing a vectorized add operation. So we're just summing up a whole bunch of numbers. We're incrementing some loop counter here, and then we're checking to see if we're done with this loop, and we're either jumping back to the top of the loop or we're exiting out of the loop. Right? So basically what we expect out of stood accumulate. Stood accumulate is just going to, in this case, sum up the contents of that vector of integers. So where we're spending most of our time makes sense, right? It makes sense in the context of what our benchmark is doing. Okay. So what else can we do with Google Benchmark, right? So we can talk about some of the other features here that are nice. So in many cases, I don't want to test just one size of a vector. I want to test to see how maybe stood accumulate fares, or maybe whatever I want to have, whatever I'm profiling. I want to test it on various input sizes. So there's a couple nice utilities for doing this. So one of them is this thing called dense range. So to this benchmark, I can say dense range. And I can give a start range, or start, a limit, and then a step size. So if I do something like 10, 12, 1, this basically says that I'm going to pass in numbers starting from 10, going to 12, and then as my step size is going to be 1 here. But you see that from the description here, the step size equals 1 is actually the default. So if you just want a step size of 1, you don't need to include it. It's implicit. So this is basically just saying that, basically to this state object, I now have access to these inputs, right? 10, 11, and 12. And so these are just going to be positional arguments in s.range 0, right? So it'll create 3 benchmarks now. So this is just some parameterization. So it'll create a benchmark with an input size of 10, a benchmark with an input size of 11, and then a benchmark with an input size of 12. And all of those will be stored at s.range 0. Now, if we had multiple inputs here, right, you might use, s.range 1 as well if you wanted the next input. But in this case, because we only have one input, this dense range, it'll be at s.range 0. So let's see what happens with our benchmark here. So we didn't need to write 3 completely different benchmarks for 3 different sizes. We can just parameterize it using something like this dense range. So let's recompile and run. And you can see now in our output, we don't just have, one benchmark run, we have 3. One for our input of 10, one for our input of 11, and one for our input of 12. And we have the timing information for all 3. Right, so that's a pretty useful feature here. But what if our input sizes get very large? Right, so what if this goes to say, 20 to 22 here? And let's recompile this and let's run. So you see, we run into a little bit of a problem here when we want to compare these numbers. All these numbers are by default in nanoseconds. And now I'm having to read, something like 606,000 nanoseconds versus 169,000 nanoseconds versus 62,000 nanoseconds. I really don't care about nanoseconds at this level. I want these numbers in something easier to read, like microseconds, right? I don't care about, if this is 54 nanoseconds versus 80 nanoseconds, right, at the very bottom. I'm mainly caring about, okay, this is 600 nanoseconds versus 170,000 nanoseconds. So let's change the scale, right? And just like we can pass in a dense range, we can also pass in the unit, right? So we can say unit is going to be benchmark, and then K, and then I can select what I want. So it can be K millisecond or K microsecond. So let's use something, or K nanosecond if we want. So let's just say K microsecond. That seems to make the most sense for this input size. So let's recompile our benchmark, and we'll run it again. And now you see we have our output times now in microseconds. So that can be a useful thing to making your output data a little bit easier to read. Another thing that's really nice to do is, or that's really nice with Google Benchmark, is that what if we don't want to run all 3 of these benchmarks every single time? Well, we don't have to. There's actually a command line flag that we can pass in to discriminate which benchmarks are actually run. So when I'm running my executable bench, I can say -- benchmark filter equals, and I can just select one of these. So I can say, I want to run accumulate bench with the input size of 2 to the 21. And now instead of running all 3, it's just going to run the case of 2 to the 21. Right? So that can be a very useful thing. Another thing we can do is we can tell Google Benchmark to run longer here. Right? So we can give it a minimum amount of time to run before it stops, rather than it just deciding some number of iterations to run. So I can say -- benchmark min time is equal to 1, and this will just make sure that the benchmark runs for at least 1 second. So we go ahead and pass that in, and you can see that by default, or at least for this run of the benchmark, originally it chose 4,000 iterations or so, but when we forced it to run for at least 1 second, now it's running close to 8,000. So this can be a good way if you really want to kind of extend out your benchmark runs and hopefully get some more stable timing results if you don't think that the preset number of iterations or the iterations that ended up being selected by the benchmark library was sufficient. Okay, so those are just a few things that you can do with Google Benchmark. I encourage you to check out the README here at github.com/google/benchmark. It contains a number of examples. There's a number of other things you can do as well. So, you're not just limited to say, dense range as far as inputs to your benchmark. You can have, very complicated custom inputs that come from functions that you define as well. So there's a number of very nice and complex things that you can do with Google Benchmark as well to create some really nice micro benchmarks. So I encourage you to check this out, check out the README here, and go through some of the examples in here. If you want to look at any of my code or any of the benchmarks that I do, so recently for some matrix multiplication benchmarks, I did this all with Google Benchmark. So you can see I wrote a number of different benchmarks here for, say, serial benchmarks, and even parallel benchmarks. So I'm using multi-threaded benchmarks as well. So there's some information about that in the Google Benchmark README. So you can check out any of this code at github.com/coffeebeforearch. But that's going to go ahead and do it for this video. Brief introduction to Google Benchmark. As always, I'm Nick, and I hope you have a nice day.